And this is the final short section on network visualization. I just want to talk for a few minutes on how to do layout, what layout might mean, and what a good layout for a graph or a network is. So let's go to the overlay PowerPoint. We used the King's Cross central line as an example of how a fixed layout might be plotted using Network X. So each of the stations here, each of the nodes, which are stations, has a fixed position. That position is defined by its latitude and longitude on a map. So there's not really any debate here in this where things go. They need to go where they are in physical real space, or roughly where they are. One of the challenges very often is that you don't have this physical layout, and you need to think of a way to do this which works for your data. So here's the exact same data, and here's King's Cross, but we've used a built-in layout tool called circular layout. So instead of collecting the positions for the drawing from the data, we've called the circular layout tool on the graph, and it's given us this layout for these nodes. You'll notice immediately that King's Cross isn't in its geographic position over here anymore. It's moved over here, but that actually otherwise all the nodes are visible, and if you move the labels up a bit, all the labels should be readable as well. A problem comes when you add the edges. So what the layout tool has done is taken all of the stations, and starting over here with Aldwych, I think, has laid them out in alphabetical order so that they're in a circle. However, the alphabetical order means that the edges, the lines connecting these different stations, are no longer in the order that they're geographically specified in. So this gives us a bit of a problem because this doesn't look anything like the tube network, and also it's taken a very simple layout, which is a circle effectively, and made it look very complicated, like a spider's web of edges and connections. So sometimes circular layout might be useful. In this case, it's not. Another type of quite common layout tool used is spring layout, or springs layout. While King's Cross appears here, which is also slightly not in the right place, but at least the edges are in some kind of order now. And this is because of the way in which this is calculated. It's an iterative algorithm which uses edges. It has springs pulling nodes together, and nodes as repelling forces, like the opposite ends of a magnet, pushing themselves apart. So what you end up with is a plot layout that has some elements of the original. So here it's in at least the right order, and they're all connected. And that's because if the edges are too far away, the strength of the spring will pull them back together. And if the nodes are too close together, the repelling forces will push them apart. So eventually you'll get a stable outcome from the springs algorithm. It iterates with the forces repeatedly until it has one. But you'll see it doesn't always work perfectly, and in these cases it's ended up with edge crossings, which are not really welcome in most graph layout systems if you don't need to have them. And also these two different iterations, which each time you call it, it'll produce a different layout, are putting King's Cross in really quite different positions. So your sense of where the network is relative to the real network might be lost. And even in an artificial network, you really want to keep some kind of spatial constancy among nodes that are the same. So you've got anchor points for your visual and cognitive systems to understand the network. An alternative is the Kamada-Kawai algorithm, and this doesn't usually generate edge crossings, certainly not for this simplicity of data. King's Cross is again in the wrong position. It should be over here if this is like vaguely similar to the London layout of the circle line. But at least it doesn't normally do edge crossings because it's based on a path length criteria as well as forces, attraction forces between nodes. So usually Kamada-Kawai is slightly better than the springs algorithm in producing an outcome. If you want to find a book that's got a discussion of these algorithms and their different performances, there's a different book by Tomasia, the Graphical Design Handbook, and they've got a chapter on force-directed layout algorithms in there. I guess we should conclude by thinking about what is it here that is a good layout. What would a good graph layout be? We don't want the hairball system. The hairballs are just incomprehensible, really. We want some kind of edge layout that works. So some of the criteria that have been proposed are reduce edge crossings. The fewer edge crossings you have, the easier it is to understand the connectivity in the network. Also, make connected paths as smooth as possible. That means sort of as straight a line as possible. So if you follow the path from X through to A, it's almost a straight line through two nodes in the network. If you try and follow the path from X to B, you'll get a bit stuck probably first, but you go across and then back down and then back across and you're there, or up and along and then back up. And so you really want connected paths, if you can, to be smooth, so you can see directly if two nodes are connected in the network. The other heuristic which people have about graphs is that there should be less than 100, probably less than 50 nodes in a graph for it to be intelligible, for you to be able to look at it and understand it, and that the number of edges coming out of each node should be limited. And I think the number was between 2 and 3, not more than that. Otherwise, again, your cognitive system gets overwhelmed with trying to work out which edges go in which directions. If you want to look at a number of publications on this, there's Cognitive Measurements of Graph Aesthetics by Colin Ware, great early paper. How do you scale networks to manage cognitive load? And Roberto Tomasi's whole book on graph drawing and visualization. So I guess that with that kind of guideline, that's the end of this short series on network layout and network visualization. It's not a solved problem by a long way, and if you're looking for a good research project, you might want to give network layout a go, particularly in 3 dimensions or 4 dimensions when you've got space and time that you want to track nodes through. Okay, well, thanks for that. That's the end of networks and Network X and our brief introduction to those tools and data types.